Hello everyone, welcome to Mtoys and Mhlongo's Mathematics and Physical Science YouTube channel. Today we're still looking at the Northern Cape Provincial Common or Control Test for March, which was done in 2023. And the focus today is question 3, which is Vertical Projectile Motion, also known as VPM, whereby we have a ball that is thrown vertically downwards with a speed of 2.5 meters per second from the top of a building, and the building is called Building A. And we have at the same time, or at the same instant, another identical ball Q that is dropped from the top of another building, which is called Building B. And Building B is 4.9 meters lower than Building A. So it is said that both the balls hit the ground at the same time. Right. And if we ignore the effects of air friction, they're asking us to define the term free fall. Now, this is straight from exam guideline. 3.1 says define free fall. Now, how do you define free fall? This is motion during which the only force acting on an object is the gravitational force. Right. Second thing, there's a note to say use only equations of motion to solve question 3.2. And in 3.2 we have 3.21 and 3.22. Calculate the time taken by ball P to hit the ground. First thing to choose here, we have to choose, according to our diagram there, we have to choose our direction. And it is best to choose the direction, or to choose a positive direction to where the object that is being projected uh, to its direction. For example, ball P is projected downwards, so it's an advice, not entirely a rule or a law, that you choose downwards to be positive to make things simpler for you in calculations. And also the other one that is dropped, if it's dropped coming from the top, then it goes downwards, and therefore downwards will be positive. So if downwards is positive, 3.21 says calculate the time taken by ball P to hit the ground. And the only information given there, as we will list it, 3.2.1, say downwards is positive. For ball P is under a building of which its displacement is, we will call it delta y of P. It has been thrown vertical downwards with about 2.5 meters per second, and it is undergoing a positive acceleration of 9.8 meters per second square. And it took it this amount of time, which we don't know. And then we don't know what was its final velocity, but we're not asked about that. We're actually looking for 4 variables to use in our equation of motion. So we have V initial, which is 2.5 meters per second. We have acceleration, which is 9.8 meters per second. We also have time, that it took from the top to the ground, which is delta t. That's what we're looking for. And we have the height of the building, which is delta y, which we will call delta y of p. Right. It is best to use an equation of motion by just looking at the information sheet or data sheet, and you just straight away write it down or copy it down. So the best one that has 1, 2, 3, 4, it's delta y is equals to vi delta t plus half a delta t squared. Now, the delta y we said is going to be delta y of the ball P, where ball P is. And the V initial is 2.5 multiplied by delta T plus half of acceleration 9.8 times delta T squared. Now we get a delta yp equal to 2.5 delta T plus 4.9, because 9.8 is 4.9. 9.8 times half is 4.9 delta T squared. So we're having two unknowns here, and we'll have to leave these as a first equation that we're going to use. Now we go to ball Q. Let's see, ball Q was dropped, and it is going downwards. It's going to hit the ground. So let's have a scenario. Dropped ball Q, say ball Q. Ball Q was dropped with a velocity 0 and delta y, which is just the delta y of ball Q. It took it, we don't know how long. Then it was undergoing the acceleration 9.8 downwards. And if we were to list our variables or information, v initial is 0. We have acceleration, which is 9.8 meters per second square. We also have delta t, which we're looking for, and delta y, which we gave as delta y of q. We're going to use the same formula. We copy it as it is from datasheet, as delta y is equals to vi delta t plus half a delta t squared. Now, another thing to note, it's important to use delta y because we are using vertical motion. Right, our delta y we said is going to be delta y of q, of which our vi is 0 times delta t plus half 9.8 delta t squared. Right, and we'll have delta yq being equal to a 4.9 delta t squared. We're given another information here that building A and building B have a difference in length or displacement of 4.9, whereby building B plus 4.9 makes up the height of building A. If we were to put that into text, it says, if we look at the displacement, delta yp versus of q, we have a space here of 4.9 meters, then that's delta yq. Mathematically, we would then say this means delta y of p is equals to delta y of q plus 4.9. meaning to say this would be our equation 2, and this would be our equation 3. So we'd have to substitute equation 1 and 2 in equation 3. Right. Remember we said delta yp is what? Delta yp is 2.5 delta t plus 4.9 delta t squared. Right. Let me first rewrite delta yp is equals to delta yq plus 4.9. Then now 2.5 delta t plus 4.9 delta t squared is equals to, we said delta yp was what? 4.9 delta t squared plus 4.9. Now these two are going to subtract each other, and we'll be left with 2.5 delta t is equals to 4.9. And then you can divide on both sides by 2.5. That we get our delta t equal to 1.96 seconds. So that is the time both the ball P and ball Q hit the ground at 1.96 seconds. Right. In 3.2.2, you say we calculate the speed with which ball Q strikes the ground. Now we're focusing on ball Q, and that is 3.2.2. Ball Q was dropped with a V initial going down, and it went down with positive 9.8 meters per second square. We want its V final. We can get its delta Y, which is delta Y of Q. All right, what else do we have? We have the time it took it to go down, which is delta T. That's 1.96 seconds. So we have two cases here. We can choose a case whereby we're just using, let's say VI 0, A 9.8 meters per second square, and we want VF, which is an unknown, and we use delta T, which is 1.96. All right, that's case 1. Then we will use the following formula: VF equals to VI plus A delta T. And we're looking for VF, and our VI is 0 plus 9.8 multiplied by 1.96, and then we get VF is equals to 19.2, then 0708, and then we round off to 19.21 meters per second. Right. Case 2, we can use delta Y of Q, which we said is going to be what? 4.9 delta T squared. And we substitute 4.9 multiplied by 1.96. So basically we're still using the time here. And then we get that their height is 18.82, the height of building B. Right. And therefore we'll be able to say V initial dropped 0 meters per second. Acceleration positive 9.8 meters per second square. V final, what we're looking for, and delta y of q is 18,82, so that we can use Vf squared is equals to Vi squared plus 2a delta y. Now Vf squared is equals to dropped 0 plus 2 times 9,8 multiplied by 18.82, and then Vf squared will be found to be equal to 368,872. Then we'll then take the square root on both sides. So our Vf squared square root will give us Vf, and then the square root of 368,872 will give us a 19,20 meters per second, which is not different from 19.21. Right, last question. Says on the same set of axes, sketch the velocity time graph for the entire motion of ball P and Q. Label the graphs as P and Q and indicate on the following the speed at which ball Q strikes the ground, the time at which ball P hits the ground. Right. The the one thing that is common in both of these, see 3.3. The one thing that is common in both of these is so the time. So we first have to label time is in seconds, and then here velocity is in meters per second. Right. They both have the time when they hit the ground, which is 1,96 seconds. We'll say it's right here. And then another thing, one ball started at 2,5 meters per second, and another ball hit the ground at 19,21 meters per second, or 19,20. And since our motion, you said it's a positive one, downwards, so our graph is going to just go a slope going up. Now, the other ball started at 0, so we'll start with the ball that started at 0, which was dropped. Right, the ball that was dropped got to 19.21 at 1, so with a ruler, you'd have to then draw a straight line getting here, and you shouldn't extend from that point. So if you have a proper ruler, I don't want to use my ruler because of time constraints. Right, then the next one started here. All right, next one started here at 2.5, then went parallel all the way up to here and stopped at 1, or well, hit the ground at 1.9. 6. One thing I am not including here is that this is for ball P, because ball P was the one that had an initial velocity of 2.5 meters per second, and then ball Q is the one that had a velocity of 0 when it started. And then when it hit the ground, it was here. Okay, thank you for watching our video. Please stay tuned for more, and we'll be posting. Please like, share, and subscribe.